Okay, so we are talking about rank of a matrix. So today we will discuss the row or in the row rank and column rank of a matrix. So suppose we have a matrix A, which is a m by n matrix. So m row n columns, and these elements are coming from a field. We can take F to be a real field also, but in general this is a field where F is a field with two operations. Okay, any field we can talk about over any field. So now, so A is a m by n matrix. So it has m rows. This is the first row, A 2 2. This is the way we. So A m 1, A m 2, A m n. This is the m by n matrix, where the elements are coming from the field. So this one is our first row. So this is our R 1, this is our second row, R 2, like this, dot dot dot. This is our, there are m rows R m, and the column, if we consider, this is our first column C 1, this is our second column C 2, like this. This is our the nth column C n. Okay. So these are the rows and columns of the matrix. So each of these rows is a n tuple. So it's a basically a element from f to the power n, because our field is n. So the ith row is A I 1, A I 2, A I n. This is ith row. I is varying from, so I is varying from 1 to m, and this is a n tuple. So this is a element from f to the power n. This is nothing but Cartesian product n times. So f cross f is nothing but the set x y, where x y are both coming from f. This is the Cartesian product 2 times, but if it is n tuple. So this is coming from f to the power n. So if f is r, this is coming from r to the power n. This is a n tuple, and similarly this is the row, this is a ith row. Now we have, and similarly a column, will come to the column. Now if you take this collection of rows, say this set R, which is R 1, R 2, there are total m rows R m. So this is a subset of, each of these element is a coming from f to the power n. So this is a subset of f to the power n. Now if you consider the space which is generating by these vectors, these are n dimensional vectors. So if you consider the space which is generating by these vectors, so that is called linear span of this. So this is nothing but linear span of this R 1, R 2, R m. So this is the all possible linear combination of this alpha 1 R 1 plus alpha 2 R 2 dot 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 alpha m R m, where alpha i's are coming from the field, all possible alpha I. So we are taking the linear combination of this, we are taking the linear span of this. So this is a subspace, and we know this is a subspace, we have shown this. We know this is a, this will again form a vector space, this linear span, this is called linear span. And we know this is a subspace, we can prove that. To to show this is a subspace, what we can do? We have to. So, this is a subset of f to the power n. Now, f to the power n is a vector space, n dimensional vector space with dimension n. Now, this is a subset. Now, when we how to prove a subset is again a vector space, then it is called subspace. So, to show this is a again a vector space, what we need to show? We need to take two element from here, and we need to take the. So, suppose we take two vector from here u and v, say u and v from this, and what we need to show? We need to show alpha u plus beta v is also belongs to this. This is a necessary and sufficient condition to become a subspace, to be a subset, to be a subspace. Now, this easily we can show this, because if you take u from this, so u is nothing but a linear combination of. So, if u is a linear span of this, so u will be written as summation of some a I r I for I is equal to 1 to m, and v will be also written as summation of b I r I is equal to 1 to m. Now, again then alpha u plus, because these are coming from L of I. Now, alpha u plus beta v, this is again can be written as summation of alpha a I plus beta b i's, then r I. So, this is some d i's. So, summation of some d I r I. So, this is also belongs to. So, this is a linear combination of the rows of the. So, this is for all u v belongs to L r, and for all alpha beta belongs to the scalar. So, this is a vector space, and this space is called the row space. So, this will again form a vector space, and this vector space is called row space. This is called, this is R of A, this is called the row space of the matrix A. And since it is a vector space, it has a dimension, and the dimension is, it is a row, it is a subspace. So, dimension of L of dimension of this R of A is called, it is it must be. So, this is a subspace. So, this is a subset of. So, dimension must be less than equal to n, it could be at most n. So, now the dimension of this is called row rank of the matrix A. Row rank of A is defined as the dimension of R of A. This is the definition of row rank. Okay. This is the definition. We define the row rank as this. Row rank is the dimension of the subspace this R of A. Okay. We can take an example. Suppose we have a matrix like this. So, 2 0 or simple matrix 1 0 1 0 1 0 1 0 0 0 Okay, 3 by 3 matrix, the identity matrix simply we take. Suppose this is the, now what are the rows? These are the rows. This is R 1, this is R 2, this is R 3. Okay. So, now what is the row space? Row space of this is the linear combination of the linear span of the this R 1, R 2, R 3. Now, here R 1, R 2, R 3 are the standard vector. So, they are 1 0 0 0 1 0 0 0 1. Now, this we know, this is are all independent vectors and this will form R 3, the real number field R 3. So, the dimension of this is 3. Okay. But our matrix is not always like easy matrix. We will take some example where we can show how to fit the, how to get the dimension of the this, how to get the. So, this is a linear, we know this is a vector space. So, we need to find the basis of this vector space. Now, since these are all 3 linearly independent vectors. So, this will form a basis. But for general matrix, these rows may not be linearly independent, we may have dependent vector in the rows, then we have to get the basis of that. So, how to get the basis of that? We will take the example. So, let us take another example which is not trivial like this one. So, suppose we take a matrix like this 2 1 4 3 3 2 6 9 1 1 2 6. So, this is a 3 by 4 matrix. So, who are the rows? These are the rows. So, we take, so what is the row space? Row space is nothing but the linear combination of these rows 2 1 4 3 6 9 these vectors 6. Now, we have to check whether these vectors can form a basis or not. If it is forming a basis, then the dimension of this this span is linear span is 3. So, to check that, what we do? We will apply the elementary row operation on this and we will convert into row echelon form, and once we convert into row echelon form, then it will give us 0 1s entities in that corresponding row equivalence matrix, and that is basically we are, when we are applying the row operation, we are basically doing the again we are doing the linear combination of the rows, because if we replace one row by the by subtracting say R j is replacing by R j plus some alpha R I plus some alpha R j. So, this is nothing but the linear combination of the rows, and exchanging 2 rows is just nothing, and applying the constant of the row is again a linear combination of the row. So, basically we will apply the row operation, elementary row operation on this matrix to reduce this to a standard form, row reduced echelon form, and to get the basis of that vector subspace. So, we will do that. So, let us take this matrix. So, we will first apply say we will apply the row operation. So, we exchange this 2 row R 1 3. So, this will become 1 1 2 6 and this will come here and this row will remain same. Then we apply some row operation R 3, we multiply this with 2 and subtract with this. So, R 3 is replacing R 3 minus 2 R 1, and again this one will do. So, we want to make this to 0. So, R 2 is replacing R 2 minus 3 R 1. So, if you do so, our matrix will become like this. So, 1. So, this first row will remain unchanged. The second row, we are multiplying 3 with this, we are subtracting with this. So, this will become 0, this is 3. So, minus 1. So, 0 minus 1, 0 minus 9, similarly 0 minus 1, 0 minus 9. Okay. So, now these two are identical. So, we can just add these two and we get. So, finally, this will, if we keep on applying this, so this will be the row reduced echelon form is 1 0 2 minus 3 0 1 0 9 0 0 0 0. So, this is our row reduced echelon form, and this will give us the basis of this vector space. So, these are the element in the basis. So, this L of R, the row space of A is nothing but linear combination of these vectors. So, 1 0 2 minus 3, only 2 vectors is there, non-zero vectors, and they are independent. So, dimension of R of A is 2. This is the row rank of A. This is the row rank of A. So, this way we will get the dimension of the vector corresponding vector space. Okay. So, similarly, we will check that, and this is the row reduced echelon form, standard form, and this operation we are doing all the linear combinations of the rows. So, that is okay. So, finally, we got the 2 linearly independent vector in the basis. This is the basis, this set will form the basis, and number of element in the basis is called dimension. So, dimension is 2. So, this is the way we find the dimension of a row space. Now, we define column space of a matrix and column rank of a matrix. So, again suppose we have a matrix like this, A 2 1, A 2 2, A 2 n dot 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 A m 1, A m 2, A m n. Now, these are the column, this is first column, this is second column, we have there are n columns, and these are. So, C I is basically C j, jth column is A 1 j, A 2 j up to A m j, this is jth column. So, this we want to show in the Cartesian product form, and this is m tuple. So, to do that we need to take the transpose of this, because the way we define the Cartesian product. So, these are all coming from F. So, F cross F we define like this, x comma y form, it is not y comma x form, but both are equivalents. So, but to get this form here we need to take the transpose of that. So, this is just a convention, notational convention. So, if you take the transpose of this, it will become this column vector will become the row vector, and then we can talk about the tuple, which is a Cartesian product of F. A 1 j, A 2 j, A m j, and this is now we can write f to the power m. Okay. So, this is f to the power m. Now, if you take this collection of this column vector, and then if you take the linear combination, linear span of this, that will give us a set which is, suppose C is the collection of this C 1 t, C 2 t, C. How many columns are there? There are n columns, C n t, and each of these columns are coming from f to the power this. Now, if you take the linear span of this, each of this is a coming from f to the power n. If you take the linear span of this, so that is nothing but the linear combination of say alpha I C I T, I is equal to R to n, all possible combinations, linear span of C, and we know the linear span forms a subspace of the corresponding vector space, and that subspace is called column space. Okay. So, this will form a subspace of f to the power m. F could be R also. If we are talking about real field, then this f is nothing but R. So, then this is a subspace of R to the power m. Okay. So, now this is a subspace. Now, this is called column space. This is called column space, and this is denoted by C of A. Column space of A, and since this is a vector space, it has a dimension. Dimension is the number of element in the basis. So, that dimension is called column rank of this. So, dimension of C of A is called column rank of A. This is the definition of the column rank. Now, this is a subspace for f to the power n, this is the m tuple over the field. So, definitely column rank will be less than m. So, definitely column rank will be less than equal to m. Okay. So, this is one observation. So, similarly, how we can find the column rank? By the similar way, we can just get the column vector. We will take that example. So, yeah. So, let us take the same example where we found the row rank of that matrix. So, let us take this example, the same matrix 2 1 4 3 3 2 6 9 1 1 2 6. Okay. So, for finding row rank, what we are doing? We are applying the row operation. This is the row equivalence form. We are applying the series of row operations, and we transfer into a what is called row reduced echelon form. Row reduced echelon form. This is a normal standard form, and this will we know we have seen this is becoming, this became of the form like this 1 0 2 minus 3 1 0 1 0 9 all are 0. This is the normal form. So, the rank of this, so we know the rank of a matrix, we will come to that theorem. The rank of a matrix is same as row rank and equal to same as column rank. But from here to get this, what we did? We did just the row operation on these rows. So, that means this is still again the linear combination of these rows. So, that means linear combination of, so if we denote this matrix as B, then the row space of A is same as row space of B, because the matrix B we got by applying the row operation on the rows of A, and row operation is nothing but we are just doing the linear combination of this. So, their linear span is same, and the rank of this matrix, because these two are only the independent vector in this space. So, the rank of this matrix is 2. rank of this space. So, now this is the row. Now, to get the column, what we do? So, this is a first column, second column like this. Okay. So, so for column we have to take the transpose. So, instead of doing that, we have to take the we can take the transpose of this matrix, then the rows, the corresponding rows will become the columns. So, if you take the transpose, this is becoming this 1 2 3 4 6 2, then 3 9 6, and now these are the columns. These are the columns, I mean transpose of the column. So, this will form the linear combination of this vector is form the column space. Now, again to get the column rank of this matrix, what we do? We have to apply the again the elementary operations. So, if you apply elementary operation on this, we will be getting like this. This is the again the row reduced echelon form. We will get 0 1 1 0 0 0 0 0 0. So, that means the column space of this matrix is same as row space of this matrix is same as row space of this matrix, and the number of independent vector here is 2. So, the column rank is equal to 2. So, we have seen the row rank also too. So, this is in general. In general, this is true that row rank and the column rank are same. So, we will just state those result. We are not going to prove it. We will supply the proof in the lecture note. So, the theorems are, we have a matrix like this. Now, the first result is row rank, this we know, row rank is less than equal to n, column rank is less than equal to n, this we have seen, and row rank is same as column rank, row rank is same as column rank, which is same as rank of the matrix. We know the rank of the matrix by taking the minors. We have seen in the last class that the determinant rank, that is called determinant rank. The minors, if the rank of a matrix is R, means we have a R order minor, non-zero minor, whereas if you take upper than R order, R plus 1 order, R plus 2 order, all the minors are 0. So, this is the rank of it, this is called determinant rank. This we can also prove that, and then the product of the matrix. So, rank of A B, if we have two matrix A B, their product multiplication is less than equal to minimum of rank of both. Actually, rank of A B is same as rank of row rank of A B, and row rank of A B can be shown as less than equal to minimum of row rank of A comma row rank of B, because this is the just the linear combination of the rows. Okay. And so, row rank is same as rank. So, that means this is less than equal to minimum of rank of A and rank of B. Okay. This we can prove it, we will give the proof in the lecture note. And the last theorem is rank of A plus B, this also we can prove using row rank or column rank, is less than equal to rank of A plus rank of B. Okay. This will prove using the row rank or column rank. So, rank of this is nothing but row rank of this. So, row rank of this is less than equal to row rank of A plus row rank of B. Okay. So, this is the this proof will be given in the lecture note. Thank you.